So can you see my screen?
No.
Okay.
Not yet.
Now it's okay, right?
Now it's visible.
Okay. You cannot see it now?
It's visible now.
Yes, okay. Okay, this is very good. Yes. I mean, next time also I have two screens, but I'm using also this ultra wide screen, and it makes a problem with Zoom. But next week I will fix another screen, so we don't have this, so we can really have better quality. And so in this slide, I want to talk about the types of machine learning models. So we need to talk about supervised and unsupervised, for example. And in supervised, it's the most common case because most of those models are developed for supervised learning. And it consists of learning to map input data to known targets. So we have, in fact, input data. We have also some targets or labels, and we have a set of examples. And we will use this the set of examples to train the model and validate the model. And it's used for classification and regression. When it's classification, we need to get some evaluation metric. And when it's regression, we need to select a different set of evaluation metrics. In case of unsupervised learning, it's about machine learning, which consists of finding some interesting transformations of input data without the help of any target. So don't have any target. And it is used for data visualizations, data compression, data denoising, or to get better understanding of the correlations which are presented in the data. Unsupervised learning is the bread and butter of data analytics. This is the most interesting, in fact, part of data analytics, in fact, and it's often a necessary step in better understanding a data set. When you have a data set and you want to understand the data set, it's better to use an unsupervised learning technique, for example, to get more depth understanding of your data set before trying to solve it using supervised learning approach. As an example, dimensionality reduction and the clustering are well-known categories of unsupervised learning. For example, we can build a model for clustering my data set, not classifying, but clustering. When it's a clustering, it's unsupervised. So we don't have a target feature. And also the dimensionality reduction as well. Dimensionality reduction, it's an unsupervised technique, which is used to reduce the dimension of your data set to simplify it so you can visualize it. For example, in Iris data set, for example, we have 4 features. So if I want to plot those 4 features, it would be very difficult to plot it in 4-dimensional space. Maybe we can ignore one of the input features and plot the dataset in 3-dimensional space. But we can use a dimensionality reduction technique, for example, and we can select 2 or 3 features out of 4 or out of any number of features. And in this case, we will try to simplify the dataset by reducing number of features. And in this case, we can easily visualize it. And we can use it to visualize the data set, and also we can use it to simplify the data and select a sample model, which can map my data set. There is also self-supervised learning, and it's supervised learning without human annotated labels. And you can think of it as supervised learning without any humans in the loop, self-supervised. And there are still also some labels involved, but they are generated from the input data, typically using some heuristic algorithm. So we can use a heuristic algorithm, which can be used to generate some labels, which can help us to use a supervised learning approach for solving this problem. So as an example, predicting the next frame in a video, for example, given best frames or the next word in a text given previous words. The last category, it's reinforcement learning, and it's in fact in reinforcement learning, it's an agent which collects or receives information about its environment and learns how to choose actions that will maximize some reward function. So it's an agent or an intelligent agent or a robot, for example, which collects information or perceives information about the surroundings and try to learn how to select an action which can maximize some reward function or minimize a cost function, for example. As an example, a neural network that looks at video game screen, for example, and outputs some game actions in order to maximize its score can be trained by reinforcement learning. So I can develop an intelligent agent which will play a game. So it will look into a video game, for example, take a print screen from a video game and try to select an action, for example, go forward, go backward, left, right, whatever, in a way which can maximize the score, for example. So this is reinforcement learning. Reinforcement learning requires simulation environment, and there are some famous simulation tools which can be used, in fact. So if you want to use reinforcement learning, for example, in an autonomous vehicle, for example, in this case, we need to simulate this vehicle, and we need to have this environment with all other factors affecting it, and try to develop this approach. In supervised learning, in fact, we learn from data, but in reinforcement learning, we learn from mistakes. So in supervised learning or unsupervised learning, we try to learn from the data. So the model would be data-driven model, for example, but in reinforcement learning, we try to learn from actions or from mistakes. We take some actions are correct, some actions are not correct. When it's correct, we will maximize the reward function. When it is wrong, we penalize it, for example. So in this case, we will try to learn from our mistakes. In classification problem, what are the types of the machine learning problems, for example? So we have binary classification, multi-class classification, multi-label classifications, and scalar regression. In binary classification, it's supervised learning since we train, since our training data set is labeled. So it's supervised, and the classification task here, where each input sample has only two classes. It could be 0 and 1, for example, or yes and no, for example, or dog and the cat. So some examples will be credit card fraud detection, for example, medical diagnosis. In medical diagnosis, you have maybe the patient has a disease or does not have a disease, for example. The spam detection, for example, it's a spam or ham, for example. So it's binary classification problems. There are many binary classification problem. So for example, iris data set, if we will select the first two classes, it will be binary classification problem. If we will select the three classes, it will be a multi-class classification problem. So in multi-class classification is a classification task where each input sample can be categorized into more than two categories or classes. And an example could be classifying a set of images of fruits, for example, which may have orange, for example, apple, and pear, for example. So in this case, we have three classes in each image, and we need to classify each image into one of those classes. So don't have only two options, but we have, for example, three options or three classes, three choices or four choices, and so on. Another example, it's classifying these handwritten digits, for example. In handwritten digits, we have digits from 0 to 9, which means it's 10 digits. Like MNIST dataset, for example. MNIST dataset has 10 digits, 0, 1, 2 until 9. So in this case, we have 10 classes. So in this case, this problem is multi-class classification. So when we build a model, the output layer, it could be, for example, the softmax layer, for example. In this case, we need to, the output should be one of 10 classes. But in case of binary classification problem, the output layer should provide us with two classes, right? Two outputs. But in case of MNIST dataset, for example, this handwritten digits, we should expect the output layer to give us one of 10 classes. We have 10 classes. And usually, when it's multi-class classification or even binary classification, maybe the output could be the probability that this example or this image belongs to this class. So maybe the output could be probability, for example. So for example, maybe the first output would be 0.5. In this case, if it's multi-class classification, the other two or other three, the summation of other two or three will be 0.5 as well. So in this case, it will be classified into that one. There is also something called the multi-label classification, and it's a classification task where each input sample can be assigned multiple labels at the same time. For instance, a given image may contain both a cat and a dog, for example, and it should be annotated both with the cat label and the dog label. And the number of labels per image is usually variable. So in each image, there will be multiple labels in each image, because you have some object which can be classified into more than one label, for example. Scalar regression, it's a task where the target is continuous scalar. For example, predicting house price. If I want to predict house prices in Oslo, for example, it's a scalar regression. So maybe you should, predict that house prices next year, it will increase by 10%, for example. So it will be continuous scalar, for example. But anyway, generally problems can be categorized into classification problems and regression problems. Classification problems and regression problems. In classification problems, it could be binary classifications, it could be multi-class classification, it could be multi-label classification. In regression problems, it's just a scalar, correct? I want to regress, for example, how much should I earn, for example, next year? So it's continuous scalar. But in classification problems, it's binary classifications, multi-class classifications, and the multi-label classification. If we need to develop a model for solving any problem, we need to have this universal workflow. So first, we need to define your problem. So for example, if you need to prepare a presentation for next week, for example, you need to use a machine learning approach to solve a problem. First, we need to define the problem. I need to define, what are the inputs, what are the outputs, what are we expecting, for example. So I need to have a good problem definition. And after that, I need to collect a data which can help me to solve this problem. So this data should be connected with my problem, should be related to this problem. So maybe someone, he need to collect a data set for developing a speech recognition tool, for example, and he will collect images. No, I need to collect something which is relevant to my problem. We need also to develop something to measure the success or fail, for example. So I need to develop a cost function, for example. And this cost function, it could be the error function, which I need to minimize. So it's very important to develop this kind of measure of success or metric, for example. I need to train a model, but when we train a model, we need to evaluate this model. So we need to develop an evaluation protocol. This is very, very important. Because if you don't have this evaluation protocol, maybe you will train a model. This model will give you very good results, but it's not evaluated. So I don't know if this model will work in other circumstances or not. So it's very important to develop an evaluation protocol to be sure that this model is not suffering from overfitting or underfitting. So how can we discover this? By developing good evaluation or validation protocol, in fact. So you can just call it its evaluation or validation protocol. I need to validate my model. Once you have your data set, you need to prepare your data. You need to clean your data. Maybe in your data, you have some missing values. For example, maybe your data has a categorical data set, for example, like iris data set, for example, and the machine learning model cannot understand the text, for example. So in this case, I need to clean my data. I need to prepare my data for machine learning model. The first step is to try to develop a benchmark or baseline model. So this baseline model, it will be a simple model which can just give you good results. It's similar to guessing, for example. So maybe 50% accuracy will be okay with this baseline model. I need to build a very, very simple model and train this model, and I hope that this model will give me just some fair results. It will be okay. And once I'm happy with the model and the model is working with my data set and everything is okay, I will try to develop this model and I will try to fine-tuning its hyperparameters. Each model has some model parameters and hyperparameters, for example. Once you have this base model, which is very simple model, and I trained the model and I validated my model and I got just maybe results, which is maybe 50%, 55%. But my system is working. I don't have any problems in my code. The next step will be to fine-tune this model. So I will try to play with the model hyperparameters to improve the performance of my model. Because I have some evaluation metric, for example, I have maybe precision, recall, accuracy. So I will try to fine-tune the model hyperparameters in order to improve those evaluation metrics. When you are happy with the response of your model, you try to document your model, for example. I need to test my model using confusion matrix, for example. I need to calculate those numbers, precision, recall, and accuracy, for example. I need to get those numbers, and I need to write down those numbers. And after that, I will deploy. When I'm happy with this model, I will try to deploy my model in my problem, for example. Maybe you need to deploy your model in an edge device, for example. So after that, he will deploy this model. So the process or the workflow will be: I have a model, and I have a training data, I collected a data, right? I will apply this data to my model to train my model. The model consists of number of parameters. It's weights and bias. It's a bunch of parameters. For example, you have this simple regression model here. So this regression model, it has some weight values and some residuals. For example, it's just a bias and the weights, in fact. So beta 0, it's bias, and the beta 1, in fact, it's weight, correct? And the input to the model will be X, which is the input features. And the output of the model will be Y, which is the actual value or the target value, for example. So in fact, each model consists of a bunch of parameters. Those parameters are weights and bias. And we have some other parameters, which is hyperparameters, such as learning rate, for example. So I will use this data set to train my model. And I will use part from this data for testing this model. So I will make some predictions, correct? And using those predictions and the actual outputs, I will try to calculate this measure of success. So I will calculate maybe the prediction error, for example, or precision and recall, and so on. So this is simply the workflow. So in this workflow, the most important is to define your problem, collect a data set which is relevant to your model, develop some measure of success or cost function which we need to minimize, try to develop your evaluations or validation protocol, and prepare your data, try to clean your data. Maybe you need to use dimensional reduction to simplify the data, for example. Maybe you need to use feature engineering to try to invent some new features which will help you to get better results. And after that, I will select a very simple model, which is a base model. I need to start with a simple one. And after that, I will try to fine-tune model parameters and the model hyperparameters. And at the end, I will document my results, and I will deploy my model at the end. Yes, so how to define your problem? So we need to answer some questions. If we need to define our problem, we need to answer this question: what is the main objectives of my problem, for example? What is my main objectives? How can we try to predict? We need to predict or classify or something. What is this dependent parameters which we will try to predict, for example? What are my target features? So we need to answer those questions because I need to collect the data. So when we define those questions, we will try to find the correct data set which will help me to develop my model. So we need to define my target feature, for example. What is my input data, for example? Is it available, those data? What kind of problem we are facing? Is it binary classifications? Is it clustering? Is it a regression problem, for example? Can our outputs be predicted given those set of inputs? There should be a kind of correlation between the inputs and the outputs. If you don't have this correlation, your model will not be able to build this kind of correlations and make correct predictions. Is the available data sufficient and informative to learn the relationship between inputs and outputs? So you need to answer those questions before collecting your data set. In the data collection is the process of collecting and measuring information on targeted variables in an established system to enable one to answer questions and evaluate outcomes. So you need to collect the data, you need to collect the right data set, for example. Maybe you can search for some benchmark data sets which can help you to solve your problem. Maybe you will have a simulation model which will be used for generating those data sets to train your model, for example. What is my data source, for example? Is it from sensors, maybe surveys, for example, interviews, box images? So you need to decide, what is my data source? You need to have good documentation. When you are writing your paper or your thesis, you need to have those informations in details. At the end, the more and the better data that we get, the better our model will perform. It's very important to collect as much data as you can. So because we train the model by data, and if you have enough data, you will have more freedom to train your model in the best way, for example. And also the data set which we are collecting, in fact, for the validation stage, we need to divide the data into one section for training, one section for validation, or for testing, for example. So it's important also to collect enough data set which can be used for training and validation. We need to choose the measure of success or the evaluation metric. And Because simply, if you cannot measure it, you cannot improve it. And this is a problem of unsupervised learning. Because in unsupervised learning, we cannot measure it, in fact. So the idea here, if you cannot measure it, you cannot improve it. So what is the considered success? For example, it could be precision. We need to increase precision. We need to increase accuracy. We need to increase recall, for example. We need to minimize biasness, for example, increase fairness, correct? So we need to define our own evaluation metric and try to improve those metrics. If you will train 2 models or 3 models, for example, you will make comparison between those models in terms of precision, accuracy, and recall, and at the end you will select the one which gives you better precision, for example. So if it is classification problem, we will have this confusion matrix, and from this confusion matrix, we will be able to calculate precision, accuracy, and recall, for example, if it's classification problem. If it is a regression problem, in this case, we need to use different evaluation metric, which could be mean squared error, for example, MSE. Mean squared error, mean absolute error. You can just select any evaluation metric for your regression problem. But just remember, in the regression problem and the classification problem, we have different types of metric. I cannot have precision, accuracy, and recall in regression, for example. So in classification problem, we need to have maybe precision, accuracy, and recall. And when it's a regression problem, we need to have something such as mean square error, mean absolute error, right? We need to develop our evaluation protocol or validation protocol. So, and this validation protocol, in fact, it's important to measure the progress of the learning process. We need to measure if I make progress or not. We can do this using this evaluation protocols. So there are famous approaches for doing this by data splitting, for example. So there are 2 approaches, or hold-out validation, for example. And in hold-out validation, we will split the data into 3 parts or portions to avoid information leak. We will have 1 part for training, 1 part for testing, and maybe 1 part of for validation. So I need to divide my data set into 2 big containers. Maybe 80% will be used for training and 20% will be used for testing. Those 20%, 80% for training, we can divide it, split it more. In fact, we can take another 10% for validation, and the validation set will be the testing set during training. Because when we are training the model, I need to test the performance of my model, because maybe training will take too much time, and maybe your system is a complex system, and it takes too much time for in each epoch. For example, it takes maybe one day, for example. So the training time, it takes time, and I need to check the performance during the training process, because maybe your system will overfit during the training and you don't know. How can we know this? We can know this by validation. I need to maybe calculate the accuracy or precision or mean square error during the validation. So when we see that the system will, or the model will start to overfit, for example, in this case, we can just stop the training process, because the system will overfit my training data set. So the validation set is very important. So this hold-out validation, we do this hold-out validation when you have enough data set, when you have a large data set. So you can sacrifice 1 part for validation. But if you have a small data set, I cannot sacrifice splitting it into training and testing. And in this case, we need to use another approach. So one more time, hold-out validation. In hold-out validation, we split the data set into 2 main parts, in fact. 1 part for training, 1 part for testing. It could be 80% for training and 20% for testing. So the training part will be used for training the model parameters, and the testing part, after completing the training, we will test the model using the testing set. But during the training, we might have some problems during the training. Maybe the system will overfit my data set, and I need to avoid this. To discover that your system is overfitting or your model is overfitting, we need to have a validation set. So in fact, we will split the training set again into 2 sections, 1 for training and 1 for validation. And the validation set, it's very small. It could be 10% of the training set, for example, and we need to keep it away for testing my system, my model, during the training process. So in each epoch, we will test we will test the accuracy of my model, for example. So in this case, we will have to, for example, error values, right? It could be prediction error, for example. So I will have the prediction error during the training, which will be a good number. In fact, it means this number will decrease, or it could be the accuracy, for example. So usually during the training process, the accuracy will increase each epoch. Because when you train your model more, the accuracy will enhance, will improve. But maybe I don't know if the model will overfit or not. You cannot discover this, in fact, in training without having a validation set. So the validation set will be used in each epoch to calculate also the accuracy. So maybe also this number will improve each epoch, but at some point it will start to decrease. And when the validation accuracy goes down, it means that my model started to overfit my training dataset. So in this case, we need to stop training. How can we stop training? We have a technique called early stopping. And in this early stopping, when the system will start to overfit the training dataset, the training process will stop. And this is very, very important because I don't want to waste the time which has been used already for training my model. Or I want to train my model until it's trained well, but I need to avoid overfitting my training dataset, because overfitting means your system will just memorize the training dataset, and it will not be able to generalize for other datasets, for example. So I need to avoid this. We can do this by splitting the training set into one part for training and one part for validation. Hold out validation, it's possible when you have enough dataset. When you don't have enough dataset, in this case, we need to use another approach, which is k-fold cross validation, for example. And in k-fold cross validation, we will split the data into k partitions or k-folds. And in each k, we will train the model with k-1 partitions and evaluate on partition number k. And we will repeat this process k times. And at the end, we will calculate the average accuracy from those k folds or k training. And this average accuracy will be the average accuracy of my model. And at the end, I will train a brand new model using the whole data set. And in this case, we are just exploited the whole data set, and we didn't sacrifice any validation set, for example. So one more time, in k-fold cross validation, we use k-fold cross validation when you have a small data set, when you have a small training data set. And in this approach, we split the data into k folds, and in each k, we will train the model using k-1, and it will be tested using k. So we will repeat this process k times, and in each time we will get an accuracy, and at the end of this process, we will calculate the average accuracy of those k models, for example. This average accuracy will be the accuracy of my model, and at the end, we will define a new model. We will initialize a new model with the same structure, but with random weights, and we will train this model using the whole data set. And we will not test the model anymore because we have the average accuracy from the k-fold cross validation protocol. There is also another approach called iterated k-fold validation with shuffling, for example, and it's the same as k-fold cross validation, but the difference is that in each, we will apply this k-fold cross validation several times, not k times, but several times, but each time we will divide the data set into k folds with shuffling. So I repeat this k-fold cross validation, for example, 10 times or 20 times, but each time, in fact, we will divide the data, we will shuffle the data, and we will divide the data into k folds. We will train with k-1 and test with k. So we can repeat this process several times. And when you repeat it several times, maybe you can get better numbers which represent reality. So instead of getting this average accuracy using a k-fold, maybe we can just repeat this k-fold maybe 10 times or 20 times. So in this case, you should get an average accuracy which represents the accuracy much better. But of course, this iterated k-fold across validation, it will take more time. We have some notes here. In classification problems, both training and testing data should be representative of the data. We need to shuffle before splitting, and all classes should be equally represented in the training and testing sets. So my data sets, my training data set should be balanced. So for example, if it's a binary classification problems, and I have some images for cats and some images for dogs, my data set should be balanced. So the same number of data images which has cats should be equal to the same number to the images which has dogs. So in this case, my data set should be balanced. Otherwise, your system will your system will be biased, or your model will be biased. Because if you are training a model to classify between cats and dogs, for example, and you have 80% of images are dogs and 20% are cats, for example, maybe this model will be biased towards dogs. And at some point, the model will classify some cats as dogs, because the model has seen more dogs than cats. So this model will be biased. And it's the same problem also. People develop the systems for hiring people, for example. So I want to hire people for some jobs, for example. So I have a system which consumes or classify CVs, for example, and select people which should take jobs. And usually those systems also are biased against women, because in fact, most of the CVs are for men, in fact. So those systems are biased because I have less women in the application. For example, if I want to select people to work in the army, people to work in mechanical engineering, for example. So in this case, most applicants are men. I mean, this is a historical data which we are using, for example. I have maybe it's dominated by men. So in this case, if I try to build a model, those models, we should expect that those models also will perform in the same way according to the historical data which we are using. And we should expect that those models will be biased also against women, correct? Because it's according to the historical data. So it's the same here. If you are collecting a data set and if you want to build a model to classify into dogs and cats, for example, we need to have a data set which is balanced data set. So I need to have the same number of images for dogs as the same number of images for cats. In this case, the system will not be biased. And also, not only this, in fact, when we try to divide the data into training and testing, for example, when we try to split, I need to have all classes are equally represented in the training and testing sets. So, for example, it's a binary classification problem, and this problem, it's dogs and cats, for example, and I split my data into training and testing, for example. So I need also those two classes to be equally represented in both training and testing, right? So, for example, in testing, in the test set, for example, if the test set is 20%, I need to have the same number of both classes are represented in the testing. So I cannot have more dogs than cats in the testing set, right? Also those, I mean, I will get precision, and those numbers will not be correct if I don't have balanced representation of each classes in the training and testing. So imagine that I have this data set for dogs and cats, for example, and I shuffled my data set, and by chance, in the training data set, for example, I have more dogs than cats in my training data set. The system will be biased. So first of all, I need to have the data set should be balanced from the beginning. So the same number of dogs should be equal to the same number of cats. And then when we shuffle and divide the data into, split the data into training and testing, also those two classes should be equally represented in both the training and the testing sets. So we don't need to shuffle if you are trying to predict future events. For example, if your data set is a time series, so in this case, we cannot shuffle, right? So we can shuffle when it's a classification problem, but when it's time series, for example, in this case, we cannot shuffle, because when you shuffle a time series, you will destroy the context of the time series. So in this case, we need to use it as it is. We cannot shuffle. So maybe I can use the first 80% for training, the next 20% for prediction, for example, or for testing, for example, but I cannot shuffle a data set, because if you shuffle the data set, you will destroy the data set. Try to shuffle a data time series and try to plot it. It will be something different, right? So in case of time series, we cannot shuffle. We need to divide it into blocks. Maybe the first 80% or the first 70% will be used for training, and the last 20% or 30% will be used for testing, for example. So in this case, we don't need to shuffle a time series. We need also to check if there are some duplicates and redundant data to avoid inaccurate learning. So because maybe my data set, I have some examples are duplicated, for example. So in this case, maybe it will make a problem because when we split the data into training and testing, maybe those examples will be in the training and the testing at the same time. So in this case, it will overestimate the performance of my model, right? So those duplicates and redundancies, in fact, it will create something called the information leak, and it will generate numbers which are not realistic. Maybe it will overestimate the model accuracy because I have the same example in the training and the same example in the testing. So it will overestimate the performance of the model or the opposite, for example, right? So we need to avoid those duplications and redundancy, redundant data into in my data set. So those notes are very important. So this balanced data set is very important. In fact, we have very nice function which we can use to split my data set. And also we have a nice function also, which will ensure that all classes are equally represented, both in the training and the testing data set. So if we need to talk about holdout validation is very, very simple. So this holdout validation, this is my data set. It's a labeled data set because we are building supervised learning model, for example. So we will split. First, we need to shuffle. This is very important to shuffle. We need to shuffle your data to be sure that it's, I mean, maybe it came in order, for example. So Iris dataset, for example, if you look into Iris dataset, the first 50 points are one class, the second 50 points are another class, for example. So if we didn't shuffle, if I will use holdout validation, for example, without shuffling, maybe maybe in the training set, the first class will be fully in. If I will sell, if in the Iris dataset, I have three classes, for example, it's a class 0, 1, and 2. So if you didn't shuffle, maybe you will have one class fully represented in the training dataset and is not represented in the validation dataset, for example. Yes, Christian?
Yeah, just a question.
Yeah.
Are you thinking about a validation set now in terms of a testing set, or an evaluation set to evaluate your loss function?
No, in fact, this one, it should be testing. Sorry, it's written here validation, but it should be test set, right?
Exactly. Okay.
Yeah.
Sorry, because sometimes validation is used as a term for evaluating the loss function during training.
Yes,
right?
yes, this is correct. Validation will be used during training, but the test set will be used at the end of the training process to evaluate my cost function, correct?
Yes.
Yes, but it's just in this graph. Maybe I need to change this graph because it's misleading. Yes.
Could be. Okay, thanks.
Yeah. So in this graph here, we will divide the data into one for training, one for testing, correct? This part for training, we need to divide it, we need to split it more again into one for training and one for validation. So we need to have another part here from the training set, which will be used for validation. And this validation set will be used to validate my cost function during training. So this is a holdout validation. In the k-fold cross validation, as we mentioned, we need to define, we need to split the data into k partitions. Imagine k equals 3, for example. And we will train the model for k-1, test for k, and we will repeat this process 3 times. Each time we will calculate the validation score or the accuracy. So at the end of this process, we will have 3 accuracies. From those 3 accuracies, for example, we will calculate the average accuracy. So at the end of this k-fold cross validation, we will have an average accuracy. And at the end, I need to define a new model and train this model using the whole data set. And we don't need to test this model or validate, calculate the accuracy again or test it again, because this model has been already validated in advance. So when you increase this k, for example, I mean, maybe k from 3 to 5, it could be nice, for example. So it's according to the size of the data set which you have. And you need to shuffle the data set into only one time. So in each k, for example, I don't need to reshuffle, but you just shuffle one time. Split the data into k folds. In the first, for k equal 1, I will train with this with k equal, for example, 2 and 3, for example, and test with k equal 1. when k equal 2, I train with k equal 1 and 3 and test with k equal 2. For k equal 3, for example, I will train the model using a k equal 1 and 2 and test with k equal 3. And each time we will calculate the accuracy, and at the end we will calculate average accuracy. So in k-fold cross validation, you need to shuffle only one time. Yes, Jose?
The second fold and the third fold, I think there's some typographical error. Maybe the first one is supposed to be training, but we still have validation.
Yeah. I mean, for k equal, yes, this is correct. I mean, it's because in the description of k-fold cross validation, we train using k minus 1 and test with k, number k. So the first one here, it's for validation, and the rest will be for training. Correct?
Yes,
So-
the second and the third. I think
Yes.
the writings, there is typographical error because we have validation.
Oh, sorry.
Suppose,
Yes.
yes.
Yes, this is correct. This is validation. I'm so sorry for this. Yes. Maybe I made this graph, in fact, and it's not correct. So this one training. This one training, validation. Oh, so sorry. I will fix it. Yes. Maybe I made this graph and I will fix this graph. So for k equal 1, we will train using k minus 1 and test with k. And we will repeat this process k times. And each time we will have a validation score or an accuracy. And at the end, we will have k accuracies. From those k accuracies, we will calculate the average accuracy. This average accuracy will be the accuracy of my model, correct? And at the end, I will initialize a model with new random numbers. I will initialize the weights, and I will train this model using the whole data set. Right? Is it okay? Yes, Hassan?
Now, one thing, I'm not sure, but is it correct what I'm saying? Like when we use this k-fold, for example, evaluation strategy, the main thing is we don't want to actually train the model. We just want to find its like best hyperparameters kind of. And then the training happens next. I mean, when we are confident that we kind of know that like if we use this range of hyperparameters, we're gonna get like something like a good model with like a good kind of accuracy or whatever measure we use. That's gonna be the whole strategy.
Yeah. Look, in hold out validation, I use this validation set because I want to discover if my model will overfit or not. Is overfitting my model or not, my data set or not. So I need to have two metric. I need to have the training accuracy and the validation accuracy, and I will plot those training accuracy and the validation accuracy in each epoch. And if you can see that the validation accuracy will start to decline, it means my model will start to overfit my training data. So in this case, I need to stop training at that point.
I think, Ibrahim, when you mentioned this, I think some methods, for example, deep neural networks, they have this built-in kind of epoch. You can pick something and use it for evaluation, but I'm not sure all models can be used in this setting. For example, having like an early termination kind of.
Yes, we have a technique called early stopping. We can use this early stopping to stop training when the model will start to overfit. But you cannot use early stopping without having a validation set. If you didn't define a validation set, early stopping will not work. Because early stopping, in fact, it will use the training accuracy and the validation accuracy. Because it needs to compare the validation accuracy with the training accuracy. And if it can see that the training accuracy, it goes up and the training and the validation accuracy is started to go down, in this case, it's an indication that my model will overfit. So when you have this situation, it will stop the training process. So this is the early stopping. So if you didn't define a validation set, you will not be able to use early stopping. So we use this validation set to just identify if my model will start to overfit or not, because I need to stop the training process and I need to get a model which can generalize. Because if your model will train, and at some point it will be able to generalize and classify very well. But if you keep training it, it will start to overfit your data. It will start to just memorize the data set. It will not, and it will not be able to to generalize, right? So how can we discover this? using the validation set, because the validation set it's a new data set which is used for testing the model during validation, during training. So in each epoch, we will calculate those two numbers. I mean, in each epoch, we will use the whole training data for training my model, updating the weights, and we will calculate the average accuracy in that epoch using the training data. And after that, in each epoch, we will use a validation set. We will send those validation set to my model, and we will see how it will classify those examples, for example, from the validation set, and we will calculate the average accuracy. So each epoch, we will have two numbers, training accuracy and validation accuracy, or training error and validation error, right? So if you can, so the early stopping technique, it will look into those two numbers each epoch, and it will stop the training process when it discovers that the model has some intentions to overfit, right? In case of k-fold cross validation, we use k-fold cross validation when we don't have big data sets, because in hold-out validation, maybe you have 20,000 images, for example. So in this case, it's okay to use 15,000 for training and 5,000 for testing, for example, right? But imagine that you have 200. 200 are very little, correct? It's a very little number, and it's difficult to use 150 for training and 50 for validation. We cannot sacrifice those 50 for validation. So in this case, we will divide the data set which we have into k-folds, right? You can define k equal 5, for example. And each time, I will train the model using 4 folds and test the model with 1 fold. And I will calculate the accuracy here. So it could be accuracy, prediction accuracy, for example, using this k-fold, for example, KISS fold, and I will repeat this process 4 times. And each time, in fact, we initialize the model, we re-initialize the weights of the model. So I don't keep the same model in each time for each k, but for each k, it will be a for loop. So for k equal 1, I will initialize the weights of the model. I will train the model using k minus 1, test it with k, calculate the average accuracy in this k. And I will repeat this process k times. So at the end, I will have 5 accuracy values. And at the end of k-fold cross validation, maybe one will be very high, one will be very low. I don't know, because the data is shuffled and it's divided into k blocks. So maybe for one block, the model accuracy will be very high. Maybe for another one, the accuracy will be low. Maybe for a third one, it will be medium, correct? I don't know. So which one should we select? We will take the average of those 5 values or k values. And this average accuracy will be the average accuracy of my model. And at the end, I will use the same model. I will train the same model using the whole data set. But before training it, I need to re-initialize the weights with random values. So it will be the same model, but with different initial values. And I will train the model using the whole data set now, so using the 200 images. So in this case, we don't need to sacrifice any images. Right? Yeah, I mean, with time, we will repeat this one from time to time. So with time, this concept will be okay. Iterated k-fold cross validation, because in statistics, for example, I can take the average of 5, but of course, if you can take the average of 50, your results will be more realistic, correct? Because of the variation. Because here in this k-fold cross validation, we split the data into k-folds, for example. So at the end, I will take the average of 3 values. But if you can take the average of 100 values, it will be more accurate. And in this case, we can use k-fold, iterated k-fold cross validation. Because in k-fold cross validation, I can repeat this process maybe 20 times or 50 times or 100 times. It will just take time. It needs more time, because each time I need to train a model, calculate the accuracy. But at the end, I will get an average accuracy, which will be more representative for my actual accuracy. Yes. For data, before training your model, now I collected my data, and we decided in which way. If my data set is large, I will use hold-out validation. As my data set is small, I will use k-fold cross validation. Maybe you need to do some data preparation also, or data pre-processing, for example. So data pre-processing, it aims at making the raw data at hand more amenable to neural network, which means maybe we need to use vectorization, normalization. We need to handle some missing values, and maybe we need to use some feature extraction, for example. You have your data set. You need to visualize your data set, for example, clean your data set, eliminate features, for example, with many missing values. If you have one column which has many missing values, in this case, maybe you can eliminate some rows. But if you have many missing values in this column, maybe it's just better to just eliminate the whole feature, right? So there are many ways, in fact, for doing this. When you eliminate a feature, for example, you will also increase the risk of losing some relevant information, because I have some input which we will eliminate. So you need to look into your data, and you need to try to fix those problems before training your model. Imputing the missing values with estimates, such as the mean value of the rest of the samples. This is one approach. So for example, we are collecting a data set, and you have one feature which is the age of people, for example. So maybe I collected a data for 100 people. Maybe 50, they provided the age. The other 50, they didn't provide the age. So in this case, I can use data imputation. So I can fill in the missing values with the average, correct? Or maybe I can just eliminate the whole column. Age, maybe age is not important. Maybe the age is not relevant, for example. But if you will eliminate the age, you will risk also losing some information, which might be important. So you need to decide. So this is something which you need to decide by yourself. Data vectorization also, we need to handling those categorical data, for example, we need to convert those categorical string values into integers, for example. So imagine that we have a data set like iris, and in this iris data set, we have 3 classes, Setosa, Virginica, and the versicolor, for example. So I need to replace each category or label with a numerical value. If you have a data set and the labels are cats and dogs, for example, my neural network will not be able to understand what cats and dogs mean. So we need to replace each category with a numerical number, right? So this is very important. Also, maybe feature scaling. We need to do some feature scaling, for example. So the learning algorithm perform much better when dealing with features that are on the same scale. Imagine that I have a data set and I have 2 features. One is age, one is income, right? So the age will be number between 0 and 100, for example, and maybe the income, it would be number between 0 and 10 million NOK. So the scale of the features is different. So in this case, I mean, the model, of course, the model will be able to deal with it, but maybe it will underestimate small feature values, and it will overestimate large numbers. It will give it more, it will pay more attention to those large numbers. So to be safe, it's better to normalize all those input features, for example. So I can divide age by 100, and I can divide, for example, income by 1 million or 10 million. So in this case, age and income will be a number between 0 and 1. Yes, Christian?
Sorry, maybe I'm asking a bit too soon. Maybe you're about to say it, but just wondering about if you have an opinion of the difference between standard normalization and min-max scaling, if one of them is the better, or
standardization and the normalization. Yeah. It's about distribution, because in normalization we don't pay attention to the distribution of the data, but we try to just put all features between 0 and 1, for example. We use min-max scaling. Correct?
Is it more used? Min-max scaling? Alternatively, you could do what's it called?
But standardization, we don't scale. In fact, we just put all. We try to fix the distribution of all data, of all features. So it has a mean of 0 and a standard deviation of 1, but not the scale. Correct? So maybe in some cases you need to focus on maybe the scale. In some other cases, maybe it's better to check maybe the distribution, for example. We assume that all features are normally distributed and has a mean of 0 and a standard deviation of 1, right?
Should you
So-
always do that, both of them? Or is
usually,
there some case where you shouldn't standardize?
So my suggestion is to develop your pipeline. And in the first pipeline, I mean, because the pipeline consists of data pre-processing, the first part. So in this first part, maybe you can test normalization, for example, and you can copy the pipeline and test the standardization and compare between your results.
Okay.
Right? So you can use, for example, normalization followed by standardization. And in the other pipeline, you have normalization, and the other third one is standardization, and just compare between your results. So you can just select the one which will give you better results.
Yeah. A lot of
So-
parameters.
Yes, but it will be organized if you can develop this pipeline. It will be easy because I can develop one pipeline and I can test many different approaches. So in fact, you don't need to define a new pipeline. In fact, it's the same pipeline, but it has 3 inputs. For example, normalization, standardization, or normalization followed by standardization. And in the model part, in the model selection, I can have 3, 4, 5 models. Correct?
Yeah.
So.
Yeah,
So at the end, I will get bunch of results and lots of data, which can be we can put it on a table, and you can compare between different approaches. So so in the paper, for example, you can just say in this example we tested normalization, comma standardization, comma, for example, normalization followed by standardization, and we got those results. So you can just have this precision recall, accuracy precision recall, for example, and put it in the table. So people readers can look into the table and they can decide by themselves that, okay, now we can see that normalization alone, it gives us better results compared to standardization, for example. So it will be nice if we can develop this pipeline, and in this pipeline, we will have different approaches in the data pre-processing part. In the model selection also, I can have 3, 4, 5 models, for example. So life will be more organized if we can develop this pipeline where we can test many different combinations of we can say that it's a hyperparameter, correct?
Yeah, exactly. So my thinking was actually to, in this view of a pipeline and to vary possible parameters like this, it's great to have some kind of intuition behind the possible variations. Like if there is a certain type of problem that usually prefers normalization or the other, then you can reduce the number of parameters because this tends to become a huge matrix. Is my experience, that there are so many things that you can try out. So what if you have 7 other parameters that you would like to alternate, and then you need to, so each time you add the parameter, you square the number of possibilities.
Yes, this is correct. Yes, this is correct. But I guess it's maybe it's a problem based. For example, if you need to select normalization or standardization, for example. So
yeah. Okay. So you should try both. It's
yes.
Short answer.
Yeah.
Okay. Thanks.
Also, we need to select some meaningful features. For example, as you mentioned, maybe the feature set is very large. Maybe we have 20 features or 100 features. So which features we should select? So there are some techniques which we can use, for example, principal component analysis and the principal component analysis, or autoencoder, for example. We can use it for feature for dimensionality reduction. I need to reduce the dimension of my data set. For example, I have 20 features, but I feel that maybe I need to compress it into maybe 5 or 4, for example. So in this case, we need to use a feature principal component analysis or autoencoder, for example. I mean, principal component is a statistical technique, but if you want to build something which can be attached to your model, because autoencoder, it's feed-forward neural network. So in fact, the first layer in my model, it could be an autoencoder, which will be used for reducing the dimension of my data set. So we will discuss about this later on, but we can use, for example, principal component analysis to reduce the dimension of my features, or an autoencoder, for example. Or there is also a nice tool in called the select k-best, for example. And this select k-best, it helps us to select the most important features from my set of features. It uses autocorrelation and it try to select the most important features for my problem. The problem in principal component analysis, the output will be principal components. So it will be something different from the input features. So the input of the principal component will be features, which we understand it has physical meaning. It could be measurements coming by sensors, for example. But the output will be principal components, which does not have any physical meaning, which is a problem, in fact. But instead of using a principal component analysis, we can select some functions which can help us to select the most important features from my input features, such as this function is called the select k-best. And the select k-best also, it's based on a statistical approach where it calculates the autocorrelation between my input features and my target feature. And we can select the most important features which have higher correlation with my input, my target feature. So select k-best, we have here a variable which we need to select. It's k, in fact. Select k-best. It's select k-best features. So we need to define k. So it's the same, also the same problem. It's a hyperparameter also. Maybe someone will select k equal 4. Maybe someone will select k equal 6. No one knows which one is better, for example. So in this case, maybe you need to use a grid search, for example. So also in your pipeline, you can use a grid search. And in this grid search, maybe it will help you to select the principal component, number of principal components. Maybe if you will use, for example, select k-best, for example, it will help you also to select maybe the most optimum feature, number of features, for example, correct? Also the hyperparameters, you can also use those search grid also for selecting maybe the learning rate, for example, number of maybe hidden layers. If you want to have number of hidden layers as a hyperparameter, you can just select, use grid search to help you to select the most optimum number of hidden layers, for example. So I mean, this equation here, in fact, it's for normalization, min-max scale, min-max scaling, for example, and in min-max scaling, it's simple. We need to, it's x minus x minimum divided by range, right? X minus x minimum divided by range. And in this case, we will convert all input features from its original scale into numbers between 0 and 1, for example. If you want to use standardization also, we try to center the features at a mean of 0 and standard deviation of 1 using this equation. So it's x minus mean value divided by standard deviation. So we need to get the mean value of this feature and the standard deviation and subtract each x from the mean value and divide it by standard deviation. So it's very, very simple. If you need to develop this baseline model, we just need to select a simple model, in fact, or a baseline model to try to create this kind of mapping between x and y, for example. And the goal here is to achieve a model which can generalize and perform well on never before seen data. This is very, very important. So to do this, in fact, we need to split the data into 3 sets, one called the training, one called the validation, and one called the test. In the training, we adjust weights, model parameters, and in the validation set, we used it to test if we used it as a test set for the training, as a test set for the training set, in fact. So we need to use this validation set for testing the model during training. From the validation error and accuracy, we can discover overfitting during the training and use techniques such as early stopping to stop training and try to avoid this overfitting problem. In the test set, we measure the generalization power of your model. So we try to avoid overfitting using the validation set, and the test set will be used for testing the generalization power of your model. So the test set is used to evaluate the final model. Model overfit, the model overfit the data when it has high model capacity or little data. And this is very important. Model capacity means your model is very huge, is very capable. So maybe you have a simple data set like MNIST. We have 150 data points, and we have 4 features, and you will develop a deep learning model, very large deep learning model, for example, for this simple data set. In this case, the model capacity will be very high because the model has millions of parameters. So it will not, the small data set will not be enough, in fact, to train those model parameters, and the model will quickly overfit the data set. It will memorize it, and it will not be able to generalize. So model capacity, it means the model has higher capacity, in fact. Capacity in terms of number of parameters. So this model has maybe thousand and millions of weights and bias, right? So maybe for the iris dataset, we need to have very simple feed-forward neural network, or maybe a perceptron, correct, to solve it, which has maybe 10 parameters or 20 parameters, for example. But if you will select a feed-forward model with hundreds and maybe thousands of parameters, so the model capacity will be very high, and in this case, the model will overfit the data set very quickly, and it will overfit. So in this case, we need to reduce the model capacity. Or you have little data, in fact. Sometimes you have small data set, and this small data set, it's not enough to help the model to train its parameters. So in this case, you need to increase the size of the data set. So one way for solving, or two ways for solving this problem, is to reduce the model capacity or increase the size of your data set. To increase the size of the data set, we have approach called the data augmentation, right? So we can use this data augmentation approach for increasing the size of the data set, or we can use another approach for reducing the model capacity, like dropout. So there is an approach called the dropout. We can use, for example, this dropout, or there are some approach to limit the model capacity, try to compress, try to stop the model, or try to reduce model capacity during the training process, so it does not overfit my dataset.
Can I ask another question?
Yes, please.
Is there a rule of thumb related to the model capacity and the dataset size? Like a number, if you take the ratio between number of parameters and number of features, or number of rows, data points?
So imagine if you have 150 data points, what should you expect? I mean, if you are selecting a model, how many parameters, for example, the same number? 150 weights?
Good question. It seems too much.
150 too much?
Yeah.
Yes, it's too much.
Is there a rule of thumb?
No, there is no rules. I didn't find any rules, in fact, but I read something, but it was a long time ago, just about the, for example, if you have a hidden, but it was a long time ago, for example, the hidden, I mean, the model structure, it should be, we should start with number of parameters, for example. Maybe the second layer, we need to increase number of units, number of neurons a little bit. So it has a bulge from the middle. And when we are close to the output, we need to reduce, go back again to, because maybe I have its binary classification problem, for example. So we need to have this bulge from the middle, right?
Yeah.
But I didn't see any. Did you see any rule of thumb?
No.
Yeah. So also it's something which I mean, we need to, because the number of parameters, it's a hyperparameter, right?
Yeah.
Which we need to set. Yes, which we need to select. But as I mean, the best practice is to start with a simple model, this baseline model. Start with a simple model, even if you will get accuracy which is not good enough, maybe 50%, 60%, and like tossing a coin, for example. So just basic guessing, for example, and after that you can start increasing the model capacity step by step until you can achieve good results. Because in fact, going from poor model to a good model, it's much easier than going from overfitting model. When your model overfit, it's very difficult to adjust what will be the model size, for example. So you need to, it will be more difficult, because it's more difficult to deal with overfitting rather than underfitting. When your model underfit your data, it can increase the complexity step by step until we can achieve good results. But the opposite will be more difficult. Yes. So it's better to start with a base model. And for example, with time, you can increase the number of hidden layers. For example, you can increase the number of neurons in each hidden layer until you can achieve good results. So in this case, you will be sure that your model will not overfit. So I can start with a model which is underfitting, rather than starting with a model with overfit and try to solve this problem later on. And we need to use early stopping when you are building your pipeline, I guess it's smart to use early stopping all time, because if you don't use it, maybe people will ask you a question: did you use early stopping, for example? Because to be sure that your model will not overfit, right? So it's a good practice to use early stopping all time.
Mm-hmm.
Yeah. So maybe your model has huge capacity, for example, and it will consume the data set very quickly, and it will overfit after 2 epoch or 3 epoch, right? Maybe if you can reduce the model capacity a little bit, it will take 10 epoch to overfit, right? So it's much safer, in fact, to use early stopping and just try to start with this baseline model instead of starting with a large model. Because, for example, today, if you want to use this transfer learning models, for example, AlexNet, for example, AlexNet, it's very huge. It has millions of parameters. If your data set is very small, it will be really, very complex to. I'm not talking about the transfer learning model, but I'm talking about the classification part, because also this model, I will use the first part as it is, I will import it and I will use it as it is, but I need to fix the bottom part, correct? Which is a classification part. This classification part also, it's according to a number of features which we are getting from the convolutional part. Maybe this part also, if it's two hidden layers, one output layer, it might also overfit quickly. So we need to develop best practices so we can try to save time in this and try to avoid this overfitting problem.
Yes.
Yes, Hassan, you have a question?
Yes, but what about this scenario? For example, I have like some data and like I use a complex deep neural networks with a lot of parameters, and at the start I try to just overfit as I can, as much as I can. The main thing I think this kind of strategy can help me with is if I can overfit on the data, it shows that the data has kind of enough information that kind of my model can overfit, because I expect a deep neural network to overfit. And also if a deep neural network, like a big complex model, can't overfit, what that is an expectation from it. We can know that maybe the data is not good enough for our task before we start even going further, because it could be that there's not much enough data, signal to noise ratio in the data, that the model, a deep neural network needs a lot of information to build the model. And if it can't overfit at the start, I think it's going to be a bad sign, maybe a sign that we might go one step back and go after a better data set or a more kind of representative data.
Yeah, but you want your model to overfit?
At the start, for example, it kind of looks counterintuitive, but I think because neural networks, they are very, very good at overfitting.
But overfitting is a problem. Overfitting means my model will memorize my data, right?
Yes.
For example, you have an exam, for example, Hassan, and I will give you one page, and I will ask you study this page, one page, just only one page, and go to the exam. You have a PhD, you are very smart, you will look into this page, you will memorize it. When you go to the exam, you got a different equation, but it's different. So for example, you studied here 5 plus 5 equal 10, for example, but in the exam, I give you question 5 plus 4. But you cannot solve 5 equal 4. I didn't see this question before, so I cannot solve it. Because you trained is a 5 plus 5 equal 10. But I didn't teach you that 5 plus 4 equal 9. So you will overfit the data, you will memorize the small data set because you have only few examples, correct? You will not be able to generalize because you studied here 2 examples or 3 examples, 5 plus 5 equal 10, maybe 6 plus 6 equal 12, but you don't have an example which is 5 plus 6 equal 11. You don't have this. So you will not be able to solve this question in the exam because you just memorize very few examples, correct? So the same problem here. My model will overfit if I have a few examples, if my data set is very small, right? Of course, you will collect a data which is relevant. So we don't need to discuss about the data because you will collect a data set which is relevant to your problem, right? So we assume that the data set is relevant to your problem. Now we are in the training process. if your model, if the data set is very small, your model will overfit, right? If your model is very complex, has high capacity, it will overfit. So how can we solve this? So we need to reduce the model capacity. There are some techniques, in fact, in the training phase. Those techniques will limit the model capacity. It will try to reduce the model capacity, correct? Like dropout. We can use dropout to limit the model capacity, for example, by 50%. The other option is to just when you select a model, try to select a simple model. Don't go for a very large model. Try to go for a simple model, a modest model, for example, a baseline model, which will give you accuracy of 60%, 70%. And after that, you can play with the hyperparameters to enhance its performance. Right?
I understood Hassan's question to be regarding the prediction value of the data set. So let's say you have a problem with overfitting, or you have a problem with not being able to fit the model at all. Then it's good to have like a toolbox, a set of statistical methods to evaluate the data set to try to see, is this all just noise, or do we expect to find some good prediction value here? Okay, yes. So he mentioned that signal to noise ratio, for example, if signal to noise ratio is too low, it means we are collecting noise, we are not collecting something visible for my problem. And so also maybe... Yeah, I'm just saying that I think this is a good or important part of the work with machine learning to be able to understand the statistics in your data set, to actually to use it before even starting to work with training. Yes. To have a good understanding of the data set. Yes, I mean, in data pre-processing, we need to visualize the data. In fact, we need to look into the data, spend more time with the data. Usually people in machine learning, they spend maybe 70% of their time with the data and the rest with the model training. So, so of course, you need to spend more time with in the data collection part to visualize the data, be using some statistical tools of really to fix the data and to be sure that there is good mapping between inputs and outputs. Maybe he can use those calculate correlations between inputs and outputs to see if there are some correlations between inputs and input features and the target feature, for example. So, yes, but I guess it's a problem based. So, maybe each one he should try to develop the tools which will help him in his project, right? Yes, so this is overfitting and underfitting. In fact, optimization is a process of adjusting a model to get best performance possible on training data. So in the learning process, we try to fit the model to my data. Generalization is how will the model perform on unseen data. So the goal is to obtain best generalization ability. For example, this model has good fit and it can generalize, in fact, so we can predict, we can regress those values with high accuracy, right? To improve the generalization, we need to get more data. Maybe we need to add weight. Those regularization techniques, it's an approach for reducing the model capacity, those L1 and L2. So in the learning process, in fact, if the model will overfit, it will penalize the learning rate with L1 and L2. So in fact, this regularization techniques, we use it to limit the model capacity or to try to reduce the learning rate during the learning process. We can use early stopping. We can use model reduction to reduce model capacity, right? So we need to reduce model capacity, for example, by reducing the model size. And also we can use dropout, for example. So we need to get more data. We need to just go and collect more data, for example, try to collect clean data, relevant data. Try to use some data augmentation techniques to increase the size of your data, for example, to reduce model capacity in the training process. You need to use L1 and L2 regularization techniques, for example. You need to use early stopping. Maybe from the beginning, when you are selecting a model, you need to reduce model capacity by reducing the model size. So maybe you need to reduce maybe one hidden layer, for example. Maybe you need to decrease the number of neurons in each hidden layer, for example. So in this case, we will try to reduce model size.
If you will use principal component analysis, in fact, you will reduce the model size by using principal component analysis, because just imagine I have a model which has 10 inputs and another model which has 5 inputs, and calculate the total number of parameters in your model. So imagine that you have a feed-forward neural network, and this feed-forward neural network has 2 inputs in the input layer, and in the output layer we have 5 in the hidden layer, and in the output layer we have 2, right? So in this case, if you have 2 inputs, how many parameters which we will have? It will be 5 times 2 plus 5 plus 2 times 5 plus 2. If you have 5 inputs, it will be 5 times 5 plus 5. I'm making this example. Can you see that example? So if you have a feed-forward neural network, for example, and if you will use principal component analysis, which will be used for dimensionality reduction, for example, and instead of using 5 input features, I will use 2 instead of 5. For the same neural network, you just calculate how much reduction in your model size. So I can just calculate it. So it will be 5 times 2 plus 5 plus 2 times 5 plus 2 equal 27 parameters. And in the second case, it will be 5 times 5 plus 5 plus 2 times 5 plus 2. So it will be 42, right? So for this sample model, can you see it, please? Maybe, I don't know if you can see it. So I mean, just imagine that you have very simple feed-forward neural network, and it has one hidden layer, and this hidden layer has 5 neurons, for example. You have output layer which has 2, and the inputs could be 5 and it could be 2. So what will be the total number of parameters? In case of 2 inputs, you will have 27 parameters and bias, and in case of 5, you will have 42. Divide 27 by 42 to see how much reduction we can get. It will be 42 minus 27 equal 15 divided by 42 times 100. So it will be 35% reduction. Can you see this number? I don't know, maybe next time we will use.
We see it.
Yes.
We see, yeah.
Yeah. So in this case, when you use principal component analysis to reduce number of parameters from 5 to 2, you can reduce the model complexity by 35%. And just imagine that you have a larger data set. You have, for example, 50 parameters, 50 features, and you will use principal component analysis. You will reduce the dimension from 50 to 5. How much reduction you will get? Maybe you will get 95% reduction. In this simple example, we reduced that by 35% by just going from 5 to 2, for example, for this simple feed-forward neural network. If the model is more complex, in fact, you can achieve more using a principal component analysis. So one approach for reducing the model capacity, just reduce number of inputs, right? By using a principal component analysis or select k-best, for example. So I have 10 features, and instead of using the 10 features, maybe some features there are some duplicates and redundancy. Maybe I don't need to use the whole set of features, and I will use select k-best, for example, and I will select 5 instead of 10. So in this case, maybe you can reduce the model capacity by 30–40%. So this is something we need to do. I mean, we need to improve generalization. We need to try to avoid overfitting by increasing the amount of data which we are collecting. If you don't have enough data, try to use some data augmentation techniques to increase the size of your data. Try to, in the learning process, try to use this L1 and L2 regularization techniques, for example. Try to use early stopping. Try to reduce the model size, right? Model capacity, for example, by reducing the model size, and use techniques such as dropout. For example, dropout is a very smart approach. Because in dropout, in fact, we can drop out 50% of the model parameters in the learning process. Each epoch, I can drop out 50%. So in this case, I will keep the model structure as it is, but I will try to reduce the model capacity by 50% if I will use dropout variable equal 0.5, right? So in this case, we will keep the same model size, but we will try to reduce its model capacity until we can train the model with good generalization capacity, for example. Maybe the next step will be try to develop a model which does better than a baseline. So your goal at this stage is to achieve statistical power. We need to develop a small model that is capable of beating this random baseline, for example. So 3 key choices to build your first working model. Choose a proper last layer activation that matches your problem. We need to select, good activation function in the last layer. If it is my problem is regression or classification, for example. We need to choose also a good loss function that matches the problem you are trying to solve. We need also to optimize, to configure my optimizer, for example. So what optimizer will you use, for example? What will its learning rate, for example? So for example, in the last layer activation function, we can use sigmoid, we can use softmax, sigmoid. When it's a binary classification problem, we can use sigmoid. When it's multi-class classification, we use softmax, for example. And the loss function in this case will be categorical cross entropy, for example. Multi-class classifications and the multi-label classification, we can use, in fact, sigmoid, or we can use softmax. If you will use softmax, you need to use this loss function. If you will use sigmoid, you need to use this kind of loss function, for example. In case of regression, maybe I don't need, I need to use linear. It's not done, but in fact, it's linear activation function. And you can use MSE, for example. So, yeah, maybe this is feature engineering also. We will go into feature engineering in the next few weeks also. Feature engineering for reading time clock, reading the time on a clock, for example. It's just an example to show you the power of feature engineering, for example. So for example, here in this example, this is image. So it's raw data, which is pixel grid, in fact, or image. So in fact, this image, we can use this image in a CNN, for example. So we can use such image for a CNN, because in CNN, we don't care about feature engineering, in fact, feature extraction or something. We can just use the raw data as it is. So this raw data will be suitable for CNN. How many inputs here? It will be the number of pixels, correct? Or it will be just the image, right? So we will deal with this image at the pixel level. So in case of using a convolutional neural network, we can just use the raw data as it is. In case of feature feed-forward neural network, maybe we can use pixel values. So in fact, this image, we can see the resolution of this image, how many pixels in this image. And we can define a feed-forward neural network which has the same number of pixels as input. So the number of inputs to this feed-forward neural network would be the number of pixels here. Or we can use some feature engineering and we can try to find the coordinates of this clock handles. So we have x1, y1, and x2, y2. For example, we have two handles here. So for x1 and y1, maybe this is the coordinates of the first one, and this is the coordinates of the second one. Right? So in this case, we can, instead of using the number of pixels, we can just use 4 inputs. So this is a feature extraction, because I will have the same information, but using a feature extraction technique. So for CNN, I will feed CNN with the whole image. In case of feed-forward neural network, I still can feed this image to the feed-forward neural network. But in this case, it will be very complex because the number of inputs will be the same as the number of pixels, right? So in this case, I will have a feed-forward neural network, which will be really very costly in the training, and it might overfit quickly. To simplify this process, maybe I need to develop a feature extraction technique which you can try to find the coordinates of the clock handles instead of using the pixels. So maybe this image is 50 times 50 pixels. So in fact, I can develop a feed-forward neural network with 50 times 50 inputs. And I can feed all those pixel values to this feed-forward neural network. But the problem here, not all the image is important. I have some features which does not make sense for me. because this is the most important part, in fact, correct? But this part is not important for me. So in this case, I will build a very complex feed-forward neural network for solving a simple problem. If you will do this, I need to collect a very large set of images to train my feed-forward neural network. Otherwise, it will overfit or underfit, correct? So it will overfit or underfit because I don't have enough data. But if you can use some feature extraction technique, for example, I can try to build a simple code which will try to provide the coordinates of the clock handles. So in this case, I will have 4 inputs. So I will build a very simple feed-forward neural network with 4 inputs instead of 50 times 50 pixels. And of course, at the end here, at the bottom here, you can try to develop simple formula, mathematical equation, for example, which will find the theta 1 and the theta 2 this angle. Theta 1 equal 45 degrees and the theta 2 equal 0. And I can just use a formula or an equation which will provide me with a time using those angles. Right? So this is white box, this is black box, correct? So if we will use this equation, mathematical equation, it will be white box because all people will be able to understand it. The input to it will be 2 values, theta 1 and the theta 2, and the output will be the time. This one, it's a black box, but if I will use those 2 features or 4 inputs, it will be easy to understand, in fact, because I know that the input to this feed-forward neural network will be the coordinates of x1, y1, x2, y2. The output will be the time. So it should be a little transparent, in fact, because a model is simple. But if I will feed this feed-forward neural network with the pixels, it will be black box. It will be very difficult for us to understand. And it's the same situation also for CNN. In case of CNN, in fact, it will try to extract the feature by itself. So in fact, we will train the CNN to extract the features. So maybe at the end of this convolutional layers, for example, maybe we will have 4 outputs. Maybe those 4 outputs will be similar to those 4 outputs here, right? So in fact, here in feed-forward neural network, we try to extract those features manually. But in case of CNN, we will extract the same set of features or different set of features automatically. So in case of CNN, we automate the feature extraction part. We automate this process. So at the end, we will have a model which has a raw pixel grid or raw image, and the output will be the approximate time, right? So the complexity of the model will be based on the complexity of the data set. If the input data will be raw, this model should be complex, should be CNN, for example. If you will try to extract features by yourself, maybe in this case, we will build a simple feed-forward neural network, or it could be transparent, it could be an equation, and in this case, maybe the input will be theta 1 and the theta 2, and it will be easy to understand how the model works. We will finish here today. How can we do the place of feature engineering in the machine learning workflow? We will try to build this workflow. So we will have the raw data, and raw data coming from different sources, different sensors, maybe some data sets, books, magazines, whatever. So we have this raw data here, raw data, and we will have this cleaning and the transformations, feature extractions, feature engineering. So maybe this feature engineering, it will be CNN, it will be dimensionality reduction, for example, using a principal component analysis. It could be select k-best, for example. It could be feature engineering. So we will combine some features to generate a super feature. So this is the feature engineering part. And after getting the most important features for my solving my problem, I will select a model, and I will train my model, and I will validate my model using the collected data and the selected validation protocol, for example. Yes. Yes. So I guess today we are finished. If you want us to discuss some of those, but we will go back to those points in practice, and from next week we will work more with examples. So yeah, do you have any question, please?
Maybe one last question.
Yes, please.
You mentioned different types of neural network architectures, methods.
Mm-hmm.
Will we focus only on that, or could we also touch into other types of algorithms like decision tree based gradient
yes.
boosting?
Yeah, we can do this. I prepared some stuff for ensemble learning, for example. So maybe we can have 1 week for ensemble learning. If you propose something, just inform me or maybe some weeks before, so I can just prepare myself and prepare material. But we have ensemble learning. I guess ensemble learning is very important. So we will try to go to those algorithms as well.
Perfect.
Yeah. So if you have any suggestions, just send it to me by email, for example, so I can prepare myself, and we can have a week, for example, to cover each topic.
Perfect.
Yes. Okay. So any other questions, please? I hope that today was a good introduction. I don't know if the amount is too much or too little, but I mean, in the next few weeks, we will go back to those specific topics, and we will work. We will work with feature extractions, for example, feature engineering techniques. We will touch it. Principal component analysis, we will use it. Autoencoder for denoising, we will go into it. Autoencoder also for dimensionality reduction, we will try to work with it as well with examples. So those points we will cover it more and more in the next few weeks. Yes. Any questions, please, or any feedback for today?
I think it was great.
Yeah, thank you very much. Thanks, Christian. Okay, so we will meet again next week, next Friday at the same time.
Yes,
So,
Professor, thank you.
Okay, so have fun until we meet next week. Yeah,
Goodbye.
thank you. Bye-bye. Bye-bye.
Thank you.
Bye.
Bye.
Bye-bye.
Goodbye.
You. Hello, Professor.
Hello?
Me and